Anyone else got a paper, by the way? Just Victor? Any other volunteers? Patrick, Evie? No.
Valentina?
I actually do, but I read it like 10 minutes ago.
All right.
Maybe I will save it for next week.
Sure. Right. 9:30, perfectly on time. Welcome everyone to Neuroccino. The way it works is anyone is welcome to come and present a paper to the best of their knowledge, tell us why they got excited about it, what the paper is about, and then we discuss it. Today we have, as promised, Victor, who's going to present a paper to us. And Victor, take it away whenever you're ready.
Hi, good morning. Thank you. So the paper I will present you here. Can everyone see it? No problem? Or is it a bit too small?
Yes, but can you make it full screen so we can nicely?
Oh, it's not full screen.
No, I see a border.
Boop, 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 boop.
It's not a big thing. It just makes the post-processing easier for me.
Yeah. Just wait a second. How do I do this?
Just increase the 150% on the top and the middle. There we go. Much better.
Okay, yeah.
Thank you.
Perfect. So this is a paper published last year, and it's of interest of me because it's linking two things that I'm doing right now. The thing I'm working on right now, and the thing that I've been working on the past, and I'm still interested in. Basically, before I started my PhD, I was doing research as a research engineer, specialized in resting state, functional imaging and analysis. And now it's as part of Michel's project, I'm still interested in resting state, and functional brain imaging, but it's in relationship with white matter and more specifically, in general, white matter lesions. And this is a paper that is part of a group of papers and a whole study linking white matter lesions with resting state functional damage or disruption. And just the title, damage to the shortest structural path between brain regions is associated with disruptions of resting state functional connectivity after stroke. So just to start, for those who are not really used to work with resting states is a way to acquire data where you ask, usually with fMRI, when you ask the participants not to do a specific task, but just to let their thoughts come and go, and to not fall asleep. That's also a requirement. But that's it. And it's a really interesting paradigm because first, because it does not depend on task, it can be done with people who have several severe behavioral troubles. So because they just have to stay calm in the machine, they don't have to do anything special. And also it's interesting because it's with this kind of paradigm, because you don't have tasks that you know exactly the onset of the different task, or for example, you cannot just look at a specific signal in the brain that you can model and then try to find in the different part of the brain. You have to just look at the data and try to correlate the data between different regions of the brain. And this is something that appears, is that different regions of the brain, distant regions of the brain, do have correlated signal between them. And these regions we call resting state networks. because they show a synchronous signal during a resting state. So they form a network. And so this kind of signal, this kind of resting state signal, is of interest because it's been shown that this functional connectivity between different parts of these resting state networks, this functional connectivity is disrupted in patients in a variety of different diseases, and especially in this case here, the stroke that create damage to the white matter does have an effect on resting state networks and the resting state connectivity between the different regions of these networks. So what the now to the paper, what they did was to look at specific measures. For example, one of them is what they call SSPL for the it's the shorter. It's a way to it's the shortest path linking two brain regions. So, for example, here you have between region A and D, you have like a direct path. So it's an SSPL of 1. Can you see my mouse? All right, thank you. Here you have, for example, in this case, you have where you have an X. You can see that the direct path has been cut by a lesion in the white matter, and this means that the relationship between A and D must go through an indirect path, and so now the SSPL is 2 because it has to go through a 2 link to reach from A to D, and so there are like direct structural disconnections here, as explained in the part A of the figure, but there are also regions that are naturally not connected with direct path, but still show resting state connectivity or resting functional connectivity. And it is assumed that it's this functional connectivity is possible through indirect structural connection. For example, on the left here, the SSPL of 2, because it requires naturally two link through the white matter, going through one region, one intermediate region, and if you disconnect one of these link, it will have to take another path, and it will increase here the SSPL to 3, as is shown in the figure. So this is one of the things that they look at to estimate. What they're interested in is to estimate the effect of these different cases, like direct link that has been disconnected, or indirect direct link that has been disconnected. So this increase in SSPL in both direct and indirect connections, what these disconnection have as effects on the resting state functional connectivity. So here is the group average lesion overlaps of the stroke patients that they study. So it's just to show you where in general are the lesions. To study the the functional connectivity, they had to use parcellation of the gray matter to be able to correlate different the signal from different regions together. And so here is an image of the parcellation. They also use a tractography atlas that they built with the HCP dataset, linking to try to link to create an atlas of structural connectivity between each of the brain regions they have. And so they can, so this is what they did. So the binarized, so they linked together all the different regions, and then they put a threshold to say, okay, this region and this region are structurally connected, and this is the red regions here on the connectivity map. And then they also, so this is the map of the direct, in fact, connection between the different regions. But here on the right part, you can see also the indirect connections. So you can find again the direct connection with an SSPL of 1 in red. And then in white, these are all the connections that can be done through just one intermediate region. And then the more regions you need to go through, the higher the SSPL, and the bluer the color is here. Then there is the effect of lesions on this structural connectivity maps matrix. And as you can see, this structural connect, if you have like a large stroke in the white matter, you will have this connection between different regions of the brain. Here it's on the right hemisphere, and you can see that in the right hemisphere you have a very high increase in disconnections, or in increase in SSPL, while in the left hemisphere there was no effect here. But there is also an effect on the connectivity between the region of the left hemisphere and the right hemisphere. So on this diagonal here on this matrix. Then this is just a summary of what kind of data they are analyzing here. So this is the patient, the connectivity, the functional connectivity matrix of a patient. So in red you have the functional connectivity, which is like synchronous between different the two regions. And blue, it's in phase opposition. So basically, there is signal going one way in one region, it's going in the other way in the other region. So it's anti-correlated, but still it's a functional connection, sort of functional connection. And so this is in blue, and in red, as I said, the functional, the positive correlation. And they remove the mean functional connectivity of the healthy group and divide by the standard deviation of the healthy group. It's just a kind of normalization of the data to get the functional connectivity Z-score of the patient. What they obtained then is that so they first looked strictly to the structural data that they had, like the structural disconnections, and to see exactly what they got without even looking first at the functional connectivity data. And they show that, well, quite expectedly, we can see that in patients, we have an increase in SSPL, so an increase in the number of intermediate regions the structural link has to go through to link two regions. With as you can see, there is a lot of basically, yeah, there is a lot of regions where there was an SSPL of 2 that are not there anymore, and now we have a lot of regions of a link that has to go with an SSPL of 7 or plus in the patients. One thing that they show also is one of the main results is that about 20% of the connectivity between the direct connectivity between the regions in the patients are impacted. Basically, it's saying that 20% of the direct connectivity has an increase in SSPL. So there is a, well, sorry, I'm a bit, I might be a bit unclear here. So I'll just stay again, take it again. So what I meant is that 20% of the direct connection between regions has been severed in general in the patients, and also 20% of the indirect link has been severed. So meaning that in each case the original path has been broken, and it requires an increase in SSPL to restore this link. Meaning that focal lesion will have a very very important effect on the connectivity inside of this patient's brain. Interestingly, as we could almost guess with the previous result. So interestingly, there is a very high correlation between the the direct disconnections and the indirect disconnections. Basically, you've got usually as many direct disconnections as indirect disconnections, which is not necessarily something that you might have expected. Maybe, well, I don't know. Yeah, sorry. And so the next the next result is just a map. So they took both direct and indirect disconnections. They put them all together to create an index saying that can be used to explain the degree of disconnection in the brain, and to correlate with the lesions in each subject. So so they did some kind of regression to get this map of where the lesion would create the more disconnection in the brain. And then there is the functional connectivity analysis, how then, and they separated both the binarized the positive correlation between regions and the negative correlations between regions, so to have two groups, and they explored whether the disconnections would have an effect on these correlations, on this functional connectivity, and they show that there is a strong effect of the direct disconnection on functional connectivity. So basically, if you have two regions that were directly connected, you will have a very strong disruption of the functional connectivity between these two regions. And it is also the case for two regions that are not directly connected. There will also be a disruption of the functional connectivity between these two regions, but it's not as strong as with direct connections. So, and you have equivalent result, although not as strong, but equivalent result with negative correlations. So you can see that the score here increases, but this is because we are looking at negative, so it's getting closer to no correlation, basically. So you have a disruption of the functional connectivity, both in direct between regions that are both direct and indirectly connected. So this all shows that the lengths of so this shows obviously that the functional connectivity relies is strongly impacted by the structural disconnection created by the white matter lesion from strokes, and specifically it shows that the direct the direct link, the direct connections are the one that will be most impactful with regard to the resting state functional connectivity. But one thing that was not really explored before was that also the indirect connection have a really strong impact. The indirect disconnection also have a strong impact on the functional connectivity. So this is basically the main results of the article, yeah. So sorry. I think that's about it. It's I think it was quite an interesting article. It's part of the whole study of resting state and white matter lesions, and it's quite interesting. But if you have questions, you're welcome to ask them.
Thank you, Victor. Not an easy paper to present. And thank you all for asking questions in the chat and for other people to chip in and answer it, so Victor could focus on his presentation. I can see one question already too. Leah, shoot.
That was before Michelle, but I cannot go. And yes, thank you, Victor. I was thinking, are there any interesting observations between the two hemispheres, kind of correlations? So if we have a lesion on one side, if the contralateral is there are some kind of correlation in terms of this measure that they evaluate. I was thinking about the diascalism.
Well, it's part of the data. Basically, you can see usually in the bottom left of the matrices, but I don't think they really looked into it deeply, but they did say that the contralateral connections usually were direct connections, and that these were the ones that were the most impacted by these disconnections. So the resting state functional connectivity was probably really impacted with this kind of disconnections. But does it answer your question, or I'm not sure?
Yes. I will look also. Thank you.
Thank you.
Lovely. Thank you. Michelle, you had a question as well.
Yeah, thank you. Super cool paper. And this is great how they managed to dissociate direct from indirect disconnection and the relationship with decrease of functional connectivity. I have a question that is related to the anatomy that they used for trying to assess this question. Is that right, that the atlas that they used didn't have subcortical regions?
I think that, yeah, they used for the functional connectivity, because it's all based on the functional connectivity at first. They used the Gordon atlas, and I don't think it has subcortical nuclei. So I'm just looking here. No, I don't think, maybe I'm wrong, but I don't think there is subcortical nuclei, so they don't look at subcortical connectivity at all. Maybe, yeah, I didn't look at this specifically, so I might be wrong. But if you look at the slides here, you can see that it's not assigned, as they say, which is what is in white. So no, so yeah, that's it. And so basically, oops, sorry. So basically, I don't think they looked at the subcortical nuclei and connections.
And so the method is great, and it's just a shame that the atlas didn't use subcortical structures. It's like the brain flattener paradox that we discussed about with Steffi. You're in this,
but yeah, I think it's because they use, with the Gordon Atlas, they use the whole surface-based functional connectivity method, and I don't know how you do. I mean, I don't think you can do surface-based with deep white, sorry, for the sub-gray matter nuclei.
And so my yes, well, yes, you can, but but maybe not at that time, or not with the Gordon parcellation. My other question was, did they try to relate the decrease of functional connectivity, the effect of decreasing functional connectivity, to the distance of the shortest path?
So sorry, I just realized that I just did what I just said is wrong, because I can see that here there is a white part in the matrix,
cool,
which is related to the gray matter nuclei. Cool. So they did do it.
Cool. So yeah, my next question was, did they try to do a correlation between the length path and that is required and or disconnected, and the reduction of functional connectivity? So like the more distant you are in terms of length, the less you'll have a decrease of functional connectivity.
I don't think I have seen this specific one.
It's like the result that is like great, and that they're showing is really that when it's direct disconnection, you have a bigger effect than when it's indirect. But we can see that the SSPL, you know, you can be further and direct. You can be like 2, 3, 4, 5. And I was just wondering whether there is a physiological effect that the more distant you are, you know, the less it will have an effect.
Yeah, that's a good question. I'm just looking because I don't remember seeing that, but because they do well. They did try to look at an index that, well, the index that of total disconnection that I talked about the fact that they put all together the disconnections to try to, it's the total number of disconnections. So yeah, they do have the index, but I think they just use it to try to regress where in the brain was the effect the strongest, but not for the
no, yeah, no problem.
Yeah,
no problem.
I hope I'm not missing. I'm not missing something. But...
And then, oh, like Patrick got a question. I'm just gonna give you a break.
Thanks. Yeah, really cool paper. Thanks for presenting. With regards to Michelle's question, I was just wondering if you wouldn't then expect like a floor effect, because basically the further apart two regions are in terms of their shortest pathways, the less they should be connected anyways. So if two regions are then, let's say, correlated with 0.1 or something, like very weakly, then you shouldn't really see such a big effect anyways. What do you guys think?
Yeah, I think yes. The furthest it is from the regions in terms of direct structural link or indirect structural link, the weakest it would, the functional connectivity should be, but there might be exceptions. I don't know. It's something that is I didn't quite see in the article. So
so as a question here. Just so if we assume the further we are, the weaker the connection, would that simply be a methodological limitation because of the distance that we have to measure? Or is there a physiological phenomenon that we can observe?
If I can comment on that, I don't think for the functional connectivity that distance really matters mathematically. So you don't have this kind of bias, because that's a correlation. So far or close, as far as you have the same profile, it's the same profile. But then the further you go, the more you interact with other regions. That's just, it's like your cycle of friend. If you go far away, you're gonna start having new friends, even if we keep our connection. And that's why the effect is less. Is like, you're still very active and you keep your profile, but we reduce our interaction.
Thanks.
But I do think that there is it's not, well, of course there is the mathematical part, but it's true that it's still brains that works for real, and that really needs, they really need for a link between regions that are functionally connected. So if it's, if the path that we observe is very long, maybe we are missing something. Maybe it's a connection that we are missing, and it's not like, oh yeah, but it's just mathematically connected because with like 6 link, and for some reason it still works. Maybe it's just no, there is a missing link literally somewhere that is not that we don't have in the structural data. And but then I think it would be really interesting to look at. But in this specific case, because they are looking at analysis of group of regions on groups of subjects, it's not as important. But in the grand scheme of things, yes, it would be interesting to look at.
Michelle has another question, I think.
It's my last question, because I can go on and on and on this, but so very interesting in the results. So decrease in functional connectivity is bigger for positive correlations than it is for negative correlations. And is this just by chance, or do you think there are like different mechanisms supporting this opposite correlation, and that's why the effect is not that big?
I think it's quite a complicated issue, because there is probably a part where it's a true difference between the positively correlated and negatively correlated regions, because maybe the positively correlated regions means that there is like there is some kind of really a real way to make them like kind of resonate together. I don't know exactly a term, but I think, yeah, resonate is like a good way to explain it. They if they move together, it's maybe easier for them to be synchronized together than if they are in a phase opposition. But at the same time, I always wonder if it might be also due to the way the data is pre-processed, because I know that there has been some troubles with interpreting some of the well, maybe not anti-correlation, but yeah, it's it's not an easy subject, I think, because it's true that the anti-correlation is here, but I can often see that it's not as well defined as the correlation. For example, if you look at resting state networks, you always have the like, for example, the positive part, where you have the, as you said, the part of the resting state network that are positively correlated, and usually we just look at that. But if you switch to the other part and look at what is negatively correlated with these resting state networks, you can see patterns, and you can see some that are related to other resting state networks. So you can say, oh, these two resting state networks are actually the kind of the same, but in opposition, or maybe they are related together, but one is active. Well, one is activated. It's not a proper term, but let's say activated with a bigger double commas. But yeah, it's. I think it's a difficult question. It's not something that I can really explain, but yeah, the negative correlation is interesting and should be further researched. But why there is more positive than negative, not sure yet.
Keeps the world balanced if there's more good. Positive is good. I have a question for you from the chat, and that is, first of all, thank you, Victor, for the presentation. Just to your last comments, what conclusions do you make with these kind of data, SSPL, in interpreting functional connectivity, resting state connectivity in patients with stroke?
Well, this is a very general question. Well, the interesting thing with this kind of disconnection is that it shows that the brain relies a lot on the direct connection between regions, but it can also, because it's not because we don't see a complete disconnection between resting states or the functional connectivity. When you have a direct disconnection, we don't see a complete destruction of the functional connectivity. It's an important decrease, but it's not only that. We can see that there is some kind of already some kind of resilience to this kind of disconnection, and the resilience is even more marked with the indirect pathways. So this is something that I find quite interesting, is that I thought that there would be like one pathway between two regions that are far apart, and that when you cut it with a brain lesion, like you would completely erase the connection, and it would wreak havoc in the brain. But as a matter of fact, there is there is a possibility to go around, and it's as a whole, the whole network is much more resilient than what I was expecting. And even more so in the case of the indirect connectivity. And it might be because they are not actually, for the data, one of my interpretation is that the reduced decrease in functional connectivity in the indirect disconnection, and the indirect path disconnection, might be because they are not looking at the right path, because they are looking at the shortest path and saying, okay, if it's disconnected, it will have an impact, and they say, okay, it's not always the case and it's not super strong, but maybe it's because it's not the shortest path that the brain is connected through in these two regions. Maybe it's somewhere else, and so sometimes they hit right, and they can see a stronger decrease in functional connectivity, and sometimes they don't get it right, and so it doesn't. And if you do the mean of all of this, we will show not as strong an effect as indirect of a direct connection. But that, to me, that's maybe a limitation. But they did say that these direct and indirect connection are, well, they say it for the direct connection at least, that these seeing where what kind of direct connection has been broken has more information about the resting state functional connectivity impact than the just the lesion size or the lesion locations. It's really about the direct path that are being cut. And in fact, now I say that, I think it's increased my point about the fact that maybe they're not looking at the right connection when they are all the time when they're looking at indirect connectivity. Maybe it's going somewhere else. So a whole field to study.
Thank you, Victor. Related to that, quick question from me before I hand over to Patrick and Michelle again. So resting state, obviously, for clinical stroke populations is a very useful tool because, especially with aphasic patients, you can get information that you cannot really get from task fMRI when patients cannot talk, for example, in the scanner or comprehend language. How long is the sequence? Is it already something that could routinely be acquired, or is it still a nice research tool but needs some trimming in terms of the acquisition time and parameters?
Well, usually nowadays resting state data, it takes about 15 minutes. The scans are about 15 minutes long. But you usually don't just get the functional data, because you need also the structural data to do registration and everything. So I don't know exactly how long you prefer a subject to be, a patient to be in the machine, what's the max limit you can have. But I'd say that for the minimal, like going inside of the machine, taking the structural scans and then the functional scans, I'd say minimum 30 minutes. So it's, to me, it might be quite long and quite short. I don't know exactly where the whole story about it. For a healthy subject, a healthy participant, it's not that long. The biggest problem is not to fall asleep if you're tired or something like that. But yeah, it's I don't know enough with that.
Yeah, it's still slightly too long for a normal clinical routine. But I don't know, for the tractography, for example, we could play the trick that we cut the sequence in two and thereby remove motion artifacts and those kind of things. But I guess we're getting closer.
Just a comment. Thing is, functional connectivity, well, functional imaging in fMRI is still very noisy, and I think it will remain very noisy. And the longer the sequence, the more noise you can try to filter out. So since we are already working with patients that have their brain like altered in some ways, if you cannot remove enough signal, you might end up with something that is not useful at all. So yeah, that's another problem.
I can see that my question kicked off the chat.
Oh my God.
So one of the questions was, but we can surely cut it down, can't we? The other comment was that that's why Mantini and others are working on predicting resting state from EEG signals. And then we got a copy and paste from the paper with all the details on the methods. Thanks for that. Questions from the room, Patrick?
Yeah, so this refers to the topic that we already tried to tackle with the negative correlations and the slightly less impact of disruptions, white matter disruptions for the negative correlations in resting state. I'm still wondering like how to interpret negative correlations. In general, you would, or it's easy to assume that positive correlation would mean something like an excitatory activation between two areas, whereas negative correlations would mean an inhibitory correlation. However, this is completely wrong, as we know, right? So from an electrophysiological standpoint, it's just not as easy as that. So I'm still wondering if it nevertheless would make sense to potentially compare the networks of negative connections or the maps with some neurotransmitter maps or receptor maps to potentially get a better hint on what might be going on there between two areas. What do you think, Victor?
I think that might be an interesting thing to look at. One fear that I have is that if you say, for example, you have two resting state networks like that are perfectly out of sync, like one is completely anti-correlated with the other. Maybe it's because, for me, you have a complex relationship between them that involves, in both cases, both excitatory and inhibitory neurotransmitter. For example, you might have some part of the networks that are exciting the opposite resting state network when they are like not well. How to say that? I have the picture in my brain where it's like if it's activated, maybe it can send like excitatory or inhibitory information, well, to the other resting state networks. But when it's, for example, when you look at the peak and trough in the activity and say this is the only thing that matters, it doesn't mean that when you are in the trough, it doesn't mean that the neurons are doing nothing and they are not activated. So it might be also a kind of activation in these neurons that are passively doing something. For example, they can be passively exciting or inhibiting something, and the opposite is true when it's on the peak of the signal. So it's really hard to predict what kind of relationship you could have between these two networks, because maybe there is a passive disconnection of other regions that disappear during an active phase, or maybe it's an active disconnection or something like that. So I think it might be a mix of a lot of different things, but maybe it's super simple and straightforward, and we just have to look. But
I doubt that it's super simple, because other people that work on that for years would have figured it out by now.
Yeah,
right?
Probably.
Yeah. The other thing I just shortly want to mention or to raise is regarding your suggestion that they might have just looked at not the correct or relevant path, but the shortest path. Well, it's really intriguing to think about that, because we would assume that, or it has been assumed that the shortest path length makes sense from a biological standpoint, right? The brain tries to conserve as much energy as possible and tries to, as all biological systems, therefore tries to use its resources ideally. Hence, there is a strong case for using the shortest path between two areas in order to interact between the areas, not going to some other distant areas. Mm-hmm. But I remember that when it comes to brain disruptions or lesions, that one argument for neuroplasticity is that you could potentially use other pathways here. As soon as the direct pathway is blocked or is inhibited for some reason, such as for a lesion. So I'm wondering if the results that you show have something to do or could be interpreted in that way, like having something to do with or suggesting that these undershadowing or usage of another more indirect path would be truly a potential mechanism for plastic recovery of the brain?
I mean, the article sure does seem to go in that direction, but I don't think that we have enough information to exactly say anything like for sure here. It's a bit tricky. I'm sorry. This
No worries, no worries.
this is a hard question.
I think we're grilling Victor out of his comfort zone now.
Sorry, it's more like did the authors tackle this? That's what I'm trying to ask here.
Yeah.
To make this fairer.
Because I don't think so.
I mean, it's also a question open for the whole plenum, right? Like, what do you guys think? Does this mean, okay, they basically, or am I just talking rubbish and this has nothing to do with one another?
So you mean the hang on, can you rephrase your question for the plasticity?
So basically, I remember, like, I'm not in plasticity, as you guys know. So I remember that one argument for a potential mechanism of recovery of a function was that if two regions are disconnected and the function itself can be recovered, it might indicate that the functional connection that is associated with the specific behavioral outcome just goes over another like mediator, meaning it increases basically its path length. So I'm wondering if their results basically could be interpreted as yeah, that's totally feasible, or if their results can't be used to basically falsify or validate this assumption.
So with plasticity, there is not just one mechanism of recovery, right? And we haven't really fully disentangled the ways the brain recovers. So taking a longer route by going a different way is one possible way to recover a function. But you could also completely shift area, shift hemisphere, and there is this dynamic dimension across time. So it may not be one mechanism for everyone, and it may not be one mechanism across time, but it might actually have a dynamic change as well. And I don't think we're at this point yet where we can completely answer that question, certainly not with one single paper.
No.
But they could have, that's a really good question, Patrick. They could have explored not only this decrease of functional connectivity in disconnected areas, but also increase of functional connectivity in the new path that is taken to try to reach a region that is not reachable because the connection is cut, and that would have been a beautiful double dissociation. But I gotta get my head around how to measure that.
I just reread the part of the discussion where they might talk about it, and they just say that well, they show that it's important to look at indirect connections, so it should be done more, basically. They don't go into details, but they say that it's a result that encourage people to look at it more in terms of brain stroke and brain lesions and white matter lesions. They don't discuss it much.
There's always more to do. Michel, you also had a question, right?
Yeah, that was more a commentary, and I really like this paper, but the idea that is behind it is a hierarchical processing of information within the network. And with Chris, when we did our software on the study of brain disconnection, we had a different vision on what functional connectivity is, which would be every network is a melody in the brain. And we tried to assess a little bit what's happening in disconnected regions, whether they are disconnected directly or indirectly in functional functional network using entropy measurements. So I will tell you how complex is the pattern of variation that is inside a region. And what we found is like when a region is disconnected directly or indirectly, the pattern become less complex, as if an instrument has been taken out or an entire melody is not played anymore in the brain. But that's because we have a different, we project a different vision of how the brain works, and that's why like the result might be contrasted.
Was that a question or a comment?
It was a comment.
Yeah.
Yeah, I mean, just showing that it actually impacts distant. I'm saying distant, but what I mean is areas that are not directly connected. So distant in terms of shortest path length. Just showing that this also is affected, like the functional connectivity here, is actually really quite a cool finding.
Yeah.
That really, well, one still has to identify whether or not this basically just shows a general principle, right? The principle that indicates the higher connected, the better is our communication in the brain overall, or if our brains, well, by losing connections, this basically affects more than just the connection itself, but really this indirect pathways. Anyway, I think now I'm losing it a bit. So probably good for a laughter at the end.
We're also coming to the end of our time today. Is there one final question, comment? No, all happy? Fantastic. Thank you so much, Victor. And thanks for putting up with us grilling you out of your comfort zone. Very much appreciated. You did super well. Thanks for the paper as well. Thank you all for joining us this morning. Have an exciting week in science, and we see you next Monday. Bye.